Hello, welcome to lecture 19. In the previous lecture, we discussed the Kelvin circulation theorem and we did not complete one important aspect, which is the barotropic term that we introduced in the Kelvin circulation theorem. And we'll see what the term barotropic means and what it means to be non-barotropic. So let's start with the definition of barotropic. A barotropic fluid So barotropic fluid is a fluid when the density and the pressure surfaces are parallel to each other. So we had briefly mentioned that barotropic fluid is, during the definition of Kelvin circulation theorem, we mentioned that barotropic fluid is where the density is only a function of pressure. So here, we're expanding on that definition. So density and pressure surfaces are parallel to each other. That is, density is only a function of pressure. And the pressure gradient force acts through the center of mass of fluid particles. Okay, so there is no net torque. So the pressure forces, the isosurfaces of pressure and density are parallel to each other, and the pressure gradient force passes through the center mass of the fluid particles, and there is no net torque. So if we draw a barotropic situation, this will be something like this. So we have the constant pressure lines, and then we draw the constant density lines. Okay, so this is a barotropic fluid. Now, what happens if the fluid is not barotropic? What is it called? And what we can, of course, it's very simple to see that now density and pressure surfaces are parallel, and if these are not parallel, this is non-barotropic. And this new term that we're introducing again is called the baroclinicity. So the fluid is called baroclinic, the property is baroclinicity. So baroclinic fluid is when, or baroclinic flows are when this is not barotropic. Of course, this is very simple. It's the density pressure surfaces are not parallel to each other, or the fluid is not barotropic. So if it's not barotropic, it is baroclinic, and you can now imagine the situation where this is true. The density is not only a function of pressure, but it is a function of other quantities in the flow. For example, the temperature or the salinity, and you can immediately now see that given that we have done the equation of state in seawater, density is a function of temperature and salinity. It is not only a function of pressure. So the atmospheric and the oceanic flows, just start with let's stick to the oceanic flows as of now. We have the density as a function of temperature and salinity. In that oceanic flow, we know that the flows is actually going to be baroclinic. It's not barotropic. The situation is something like this. So if we have the constant density lines and the constant pressure lines, we'll have to draw these lines which are not parallel, not parallel to each other, so they will be something like this. They will be at an angle, the constant density lines and constant pressure lines, and this gives rise to a net torque. Okay, and you can see that why Kelvin's circulation theorem may not exactly hold in ocean, because the flow is not barotropic. This is the oceanic flow is baroclinic because the density of the fluid, we know by the equation of state, is dependent also on temperature and salinity, and not only on pressure, which is the condition for barotropicity. And that condition is important for the Kelvin circulation theorem to hold. So even though away from the boundaries we can assume it to be inviscid, and that is an incompressible flow, and only gravity is acting on that, assuming that that's the only force which is acting, still we will find that given the fact that density is now dependent on quantities other than pressure, we will find that the Kelvin circulation theorem does not hold exactly. So the Kelvin circulation theorem is also important. The reason why we derive this is important to have an understanding of how vorticity is generated. So the Kelvin circulation theorem gave us an idea of that under certain conditions the circulation is conserved. Now this statement of the Kelvin circulation theorem also gives us an idea of how vorticity can be generated. So we can generate vorticity in a flow with non-conservative body forces non-conservative forces non-barotropic condition, that is pressure is not only a function of density is not only a function of pressure, and non-zero viscous forces. And we'll see from the vorticity equation how each of these terms play a role. So let's derive the vorticity equation. So we'll start with the momentum equation. So we have now written down this form of the momentum equation multiple times. So this is a conservative body force, which is the gravitational force which is acting on the system. So we'll use some vector identities. So this product, the nonlinear terms can be expanded as okay. So we're expanding the nonlinear term u dot del u as this form, and we take the curl of the momentum equation. So why we are taking the curl of the momentum equation is because vorticity is equal to the curl of the velocity field, and hence if you are to get the vorticity from the momentum equation which has u, you'll have to take the curl of the momentum equation, because that will give us vorticity, and that is the reason why we're taking the curl of the momentum equation. So once you take the curl of the momentum equation, so I'm just expanding and including this expansion, curl of the momentum equation. And so first term is simply this, the curl of u, which is the partial time derivative of the quantity omega, which is the vorticity, and then the curl of this other thing, this term that we have expanded now. Okay, so we'll just replace it. So these are the terms on the left hand side, and on the right hand side we have so this is phi. I mean, I'm just writing phi as the gravitational potential here. I mean, this symbol can also be used for other purposes, but for this context, for this derivation, I'm using it as a gravitational potential. And the last term is this one. Okay, so this is the phi is the gravitational potential. We have also introduced during the Kelvin's circulation theorem derivation. Now the curl of the gradient of a scalar function is 0, hence the second term, that is the gravitational potential term, goes to 0, and we use the fact that these two operators the order of the operations can be exchanged, and this can be proven. We have del omega by del t minus del cross u cross omega equal to the curl of minus 1 by rho gradient of p plus nu Laplacian of the vorticity vector. Okay, now we're expanding this term here. This term can be expanded as del cross u cross omega. It's a vector identity, so we can omega dot del u minus omega del dot u plus u del dot omega minus u dot del omega. Okay, now the fact that the divergence of the velocity field and the vorticity field goes to 0, we had derived both of these. This term is just, the second term just reduces to this one minus this one. Okay, so the vorticity equation, I mean, just writing down a slightly simplified form, gradient of p by rho plus nu del square omega. Okay, now we again use vector identity here. This term using the identity del cross, so rather let's use a different ink. So the curl of a vector over scalar is C, that is a scalar, and del cross A minus gradient of the scalar cross the vector A. Gradient of the scalar makes it a vector, so we can take a cross product. That is why it's valid. So using this vector identity, on the first term, now on the right hand side, what we get is now we have combined u dot del omega into this total derivative, including this partial derivative in time. I mean, these two terms are being combined in the total derivative. In the total derivative, capital dt of omega minus omega dot del u equal to 1 by rho square gradient of rho cross gradient of p plus nu del square omega, using the vector identity. This equation is the vorticity equation. Okay, so this equation gives us an evolution of the vorticity field in the system. Okay, so vorticity is a vector quantity and it will evolve, and this is the time evolution, time and space evolution of the vorticity in a fluid. So now let's see what each of these terms mean. So this total derivative of this vorticity, so this is the total derivative of vorticity. So this is the change due to both change due to temporal and advective components. We're just describing the various terms of the vorticity equation. The last term, nu del square omega, so this is the term that represents the molecular diffusion of omega. Okay, so this term represents the molecular diffusion of omega. So this is similar to the molecular diffusion of viscosity. I mean, it's exactly the same process, that is viscosity kills the gradient in the vorticity and as well as the velocity. So this has analogy in the momentum equation. The total derivative also has analogy in the momentum equation. So there are two terms in this vorticity equation which is unfamiliar at this point, and you can of course see which are these two terms. So the first term is this omega dot del u, and the second term is this term, and we'll see what each of these terms mean and how they are responsible for generation of vorticity. So these don't appear in the momentum equation, these appear especially in the vorticity equation, and that is the reason why we need to do a simple discussion what each of these terms mean. So del rho cross del p. So this is the term that we'll start with. First of all, this term is the generation of vorticity. I mean, represents or contributes generation of vorticity when gradient of P is not parallel to gradient of rho. That is, the surfaces of constant pressure and constant density are not parallel to each other. And if you recall, we had already discussed this special situation, or rather actually it's actually very prevalent in ocean. So this situation is baroclinicity. That is, the constant pressure dense surfaces are not parallel to the constant density surfaces, and this misalignment gives rise to a net torque, and this is responsible for generation of vorticity in fluids where the density is not only a function of pressure. Density is a function of other things, for example temperature, salinity, or other concentrations that are present in the or other solutes which are present in um, um, the flow. Okay, so this is the baroclinic generation of vorticity. So this term represents the baroclinic generation of vorticity. If density were only a function of pressure, then gradient of P cross gradient of rho would have been 0, and there would have been no contribution from the baroclinic term. So this is the baroclinic term, and this will actually go to 0 for a barotropic fluid. Now this other term, omega dot del U. So this is a term that does not appear in the momentum equation, and hence this is something that we should discuss. So if we write omega dot del U as omega, so limit AB going to 0, I'll just tell you in a moment what is AB. We are writing this the U dot del U term as this one. So AB are neighboring points on a vortex line. So you have a vortex line which has 2 points A and B, and omega is the vector which is tangent to the vortex line at each and every point, and del U is the velocity at of the fluid. So del U is the velocity of the fluid at B relative to that at A. Okay, this is a vortex line. A and B are neighboring points, and del U is the velocity field, velocity at B relative to that at A. So now the contribution to the fractional rate of change of the vorticity that is 1 over mod omega del omega del T is same as the fractional rate of the change of the material element AB. So the material line element AB. The part of change in omega part of the change in this vorticity omega comes from the rigid rotation comes from the rigid rotation of the line element that we drew previously, comes from the rotation with line element, which is because of the which is due to the component of delta u normal to omega. Okay, that is the component which will give rise to rotation. I mean, this will remove, I mean, it will give a orthogonal direction, orthogonal velocity to that line element, and part due to extension or contraction of the line element which is now, you might have already guessed, due to the component of delta u parallel to omega. Okay, so extension and contraction is because of the velocity field which is parallel to the vortex line, whereas the rotation is due to the component which is normal to the vortex line. And when I say vortex line, it automatically means the vorticity vector, because vorticity vector is always tangential to the vortex line. Hence, this term denotes changes to vorticity due to stretching and tilting of vortex lines. Okay, so this is the term that we have been discussing. This omega dot del u is the term that denotes the changes, denotes the generation, the change in the vorticity due to stretching and tilting of the vortex lines. This is not present in the momentum equation. This is a new term that is there in the vorticity equation, and hence we are discussing its property. Okay, in case of a 2D flow, and let's assume it's a barotropic flow. In case of a 2D barotropic flow, omega dot del u is equal to 0. Convince yourself. This is for you to work this out. And for barotropicity, we have del rho times the curl of the cross product of del rho and a gradient of rho and gradient of p is equal to 0. Of course, these are scalar quantities, so only only gradient operator can act on them. It makes no sense to operate del operator, which is a vector operator, and hence the vorticity equation boils down to nu del square omega. Okay, now there is only one component, so we can write it as a scalar equation. Okay, so this has the same form as the equation of a conserved quantity that is advected and diffused in the fluid. So this is this is similar to an advection diffusion equation. Advection diffusion equation of a conserved quantity, conserved scalar here in this case, Where is the advection coming from? Advection is included in this term. There is a term which is u dot del omega, which we have condensed into this material derivative, and hence this is an advection diffusion equation. This is diffusion is created this by this viscosity. Viscosity is killing gradients in vorticity. However, if the fluid is baroclinic, one component of del rho cross del p, again gradient of rho cross gradient of p, okay, will contribute to vorticity. So this is again for you to make sure that this is what that happens. Thank you.